Okay, so let's goof around with quadratic functions. A quadratic function is a function in particular, and functions have inputs and outputs. And the way we record those usually is I write f of x, where x sort of is just a placeholder for the input. And then what we do over here is we write down sort of a rule that tells me how to take the input, multiply by stuff, add by stuff, whatever, and get the output. So a quadratic would have a rule like maybe 2 times x squared. By order of operations, we do the x squared first, plus 6x plus 4. And to be a quadratic, it has to be describable as the sum of a constant term, a linear term, or a number times the input, plus a constant times the input squared. Okay? So, now the nice thing about quadratics is you can have any real input you want. In math speak we say the domain is all real numbers, and there's lots of fancy way to write that. But I'll just write all real numbers. And the interesting thing about the range is the list of possible outputs. So this is the list of all possible inputs. Nice thing about quadratics is the range is always all real numbers. The range is pretty easy to read off too if it's in the right form. But there's a couple of different forms that quadratics can be written in. Okay, so this is the form where you just have a quadratic coefficient times x squared, a linear coefficient times x, and a constant. This is the form that's best if you're trying to figure out what input you need to get an output of 0. And of course, if you're going to graph that, it's going to be rather convenient because those would be the places where it crosses the x-axis. So, of course, you're going to move right and left to indicate what your input is. So, for instance, if my input was 1, I'd sort of move over here to 1, and I'd say, well, if I put in 1 here, the rule would be 2 times 1 squared plus 6 times 1 plus 4. By order of operations, I'm going to do the exponent first, so that's 1. Then I do multiplication second, so 2 times 1, and then I do 6 times 1, so just being slightly pedantic here, we do that. Then, last but not least, I do addition and subtraction, so you add those together and you get 12. So if I had 12 hash marks here, use your imagination, that's 12 hash marks, I have this point 1, 12, and that dot is going to be on the graph of this equation. Now, if I were going to really graph all the possible inputs, I would be here forever because any real number can be an input. So we could do 1, we could do 2, we could do 3, I could do 1.0147938, or anything else I wanted to, right? But if you're trying to get a picture for what this looks like, it would be really cool to figure out what input you could put in to get out an output of 0. Okay, and there's sort of a nice trick to doing that, and we call it factorization. So I want to figure out where this thing is equal to 0. I'm trying to figure out the x values that do that. And first what I'm going to do is I'm going to factor out any constants that I have in common. So notice all these terms have a 2. So I set it up so that if somebody were trying to practice the distributive property, they could distribute that 2 to all of my terms and get back where I started, right? Now, this term here, I can also factor. This is a quadratic, and many quadratics can be factored into the product of two linear terms. Now here's how it works. If let's just be wildly optimistic and pretend like I had two linear terms. By linear terms, I mean something x plus maybe some constant here plus some constant there. Well, if I had that, let's be optimistic, and I were trying to get back to where I started, I'd multiply x times x, I'd get x squared. Well, that would be marvelous. Then I'd multiply x. X would distribute to this term. That would give me some number of x's. This would distribute to that term, give me some number of x's. Those two things ought to add up to 3. And of course, the constant times the constant should add to 2. But you probably already knew that. So what times what multiplies to 2? Sorry, they multiply to 2. 2 and 1, and lo and behold, x times 1 plus 2 times x adds to 3, so I get that factorization. Isn't that convenient? Well, there's something called the zero product property that says if you have real numbers that multiply to 0, one of those numbers must be 0. So 2 times something equals 0 tells me that the something is 0. So either this piece must really physically be 0, in other words, x plus 2 must be 0, or x plus 1 must be 0. Well, isn't that convenient? Because if x plus 2 equals 0, that means x equals -2. If x plus 1 is 0, x must equal -1. So that tells me two things. One, it tells me that if my input, sort of working back up, if my input was -1, if you put -1 there, this term would be 0. That means the product would be 0. That means that would be 0. That means that would be 0. So if the input is -1 or -2, the output is 0. So if the input is -1, the output would be 0. If the input is -2, the output would be 0. It tells me another thing, and that is that there is no other input that will give me a value of 0 as my output. Okay, so now I guess this is the point where I sort of generalize wildly and say, wouldn't it be nice if, knowing those two dots, you knew the shape of a quadratic, which, truth be known, you probably do already, and you could just draw that quadratic. And in fact, quadratics generally come in one shape in two varieties. There's either the parabola cupped up or the parabola cupped down. This one's a parabola cupped upwards. And there you have the shape. These points are quite useful. So, why on earth would I say that it's that shape? Well, I suppose you'd have to go and you'd have to make an argument from another direction. Okay, so there's sort of two forms that's useful for a parabola. There's this form, but then there's also this other form. And the other form is what sometimes people call standard form, and it comes basically from starting with the simplest parabola you could imagine. Okay, let's imagine we had x squared. Well, that's a parabola. It happens to have a constant x term, which is 0, and a constant term that's 0. So isn't that fun? But I said it's a parabola. The graph is a parabola. I guess the shape is a parabola. It's a quadratic function. So what's that look like? Well, if I plugged in, and I could do a fun little table over here, if my input was 0, my output would be 0. Wouldn't that be marvelous? If my input was 1, my output would be 1. If my input was -1, my output would be 1. So 0, 0, 1, 1, -1, 1. If my input was 2, my output would be 4. If my input was -2, my output would be 4. It's a very optimistic function, always these positive values. And you can sort of see that I'm allowed to plug in, say, 1/2 too. If I plugged in 1/2, I'd get 1/4 as my height or my output, and so on. And you'd see that I'd get this smiley face. Well, there are a couple of things that you can do, and it turns out, actually there are exactly 3 things you can do, and it turns out really using those 3 things you can get to any other quadratic function. Well, for one, there's no reason why I couldn't shift this whole shape up. In other words, my outputs could be increased. So how about I have f of x equals x squared plus 2? Well, that means my inputs would be the same, but all the outputs would be upgraded by 2. So if that's 2, all the outputs would be upgraded by 2, so you get that same shape a little higher. Isn't it marvelous? If you want to go down 2, you could subtract 2. That would be just as marvelous. Well, so I can now go up and down. Isn't that great? I can also go left and right, but it's a little sneakier. So let's suppose to go up and down, I need to just add something at the end. If I need to go right and left, well, I need to input, let me draw my picture and sort of tell you my vision for what I'm going to do. I'm going to input x equals, say, 3, but I want the function to treat it as if I were inputting 0 here, so I get that height. And then, since I'm trying to move the function right, I want to input 4, and I want the function to treat it as if I were inputting 1. So to move the function right, I have to get it to treat 3 like 0. How do I describe a function, f of x? Notice all my functions are called f of x. That's because I'm not very creative. So I need to take an input, x, and I need the function to treat it like 0 when x is 3. Well, how do you do that? You take 3 away from x, then you do the exact same thing you did up here. Aha, isn't that fun? So now you can see if I plugged in a 3, if my input was a 3, my output, 3 minus 3 inside parentheses, would give me 0 squared plus 2. So now, I suppose I'm taking this right here and I'm shifting it right by 3. And if I plugged in 4, you'd get a height of 3, so the point 4, 3 comes into play, and that's marvelous. So I can shift it up and down, and then I can shift it right, and if you put in a plus 3, you could shift the whole thing left. So up, down, right, left. Isn't that great? So you can sort of move this to be wherever you want. And really, there's only one thing left that you could think of doing with a quadratic function, and that's what if you wanted to make this parabola narrower or flatter, or maybe you wanted to make it actually go down instead of up. Well, those are all really, if you treat this point, that point, by the way, that lowest point in all of these is called the vertex. That point that's going to get your x squared term having no output. If you treat that as sort of the all-important point, that's the point where this contributes nothing, and you want to go up more steeply to the right and the left of that, well here's what you do. So we'll take this, and let's say we want to go up really steeply. I'll put in f of x equals 5x minus 3 squared plus 2. Well, here's the funny thing. You know, if you were doing a table of values here and you plugged in x equals 3, the 5 would do a whole lot of nothing, because that would be 0, you'd multiply, you'd just get 2. So it has the same vertex. That's the place where it goes from increasing to decreasing. That's one way to think about it. And that would still be at the point 3, 2. Okay? But the catch is, as soon as I increase from that, let's say I go up to 4 and use 4 as my input, 4 minus 3 is 1, square it, you get 1. Now I get 1 times 5 plus 7. So whereas in this picture, I went up by 1 when I went over 1, now I'm going to go over 1, and I'm going to end up being 5 higher. So this is a very high parabola. And if I go 1 farther, now instead of going 5, here I'd go 1 higher, then I'd go 3 higher. You could check that. Here you go 5 higher, then what is it? It's 20 higher, I guess, going from here to the next dot, so the next unit. And you can test me. Maybe you should be suspicious of things you haven't tested yourself. Okay, and then if we go down 1, if we plug in 2, I get 2 minus 3. That's negative 1. Square it, it's 1. and I get 5 plus 2 the other direction too, and you get this shape actually made more steep. Now if you put in a 1/5 there, these things, instead of going up 5 on that first step over, they would only go up 1/5, and you get a really flat shape. Well, what if you just aren't feeling optimistic, and instead of having your parabola go up, you want a parabola to go down? Well, I suppose you could put in a -2. What would that do? That would give you the same vertex, right? That doesn't change anything if that term's 0. But then if you go 1 to the right, you're actually going to go down 2. And if you go 1 to the left, you're going to go down 2. So you would get a parabola like that. So the basic shape parabolas have is either a smile or a frown. How do you tell, how would you tell which ones were smiles and which ones were frowns? That, of course, is slightly less than technical, but who cares? It's true. So notice that here, or even technically here, because the lead coefficient here is technically 1, if you expanded all this out, the term in front of your x squared term would be positive, it would be positive, here it would be negative. Now I told you that clear back up here, this was going to be cupped upward. Well, I really was just looking at the 2, saying, hey, it's going to be positive, that'll be the shape. These 3 things that we talked about here, shifting it up and down, shifting it right and left, and scaling it or stretching it, are the only 3 things that you can do to a quadratic function. So what do we have here? We have 2 forms, and the 2 forms are very useful, but for different things. This is called standard form, and it's really easy to read off the vertex here, okay? Because the vertex in this form, this piece, whatever you're subtracting here, is the x value of the vertex, and whatever you're adding here is the y value of the vertex. And this tells you whether it's cupped upwards or whether it's cupped downwards and how steeply it's cupped upwards and downwards. But it's a heck of a lot easier if you have it like this to factor it and figure out where it actually crosses that line. So there's these 2 forms. I think they call this the general form. The general form is easier for finding the zeros. The standard form is easier for finding the vertex. There's a you might not care, but there's a kind of a cute little trick up here for finding the vertex. If you call this coefficient A, that B, and that C, just so we can talk about them in general, the vertex is always going to have x value. What's the x value of the vertex going to be? You see this still has a vertex over here, even though we haven't really talked about it. The vertex is always going to be at x equals -b over 2a, and in this case that's -6 over 2 times 2. So in our particular case that's -6 over 4. What is that? I suppose that's -1.5. Shocking! Our vertex is actually at -1.5. The x value is -1.5. So there is a way to find it up here, but it's sort of easier to see it down here. And what? For extra credit, you can think about the quadratic formula and think about how this actually falls out of the quadratic formula. Lots of fun. Okay, see ya.